Again, thanks. Heavenly Father, excuse me, thank you for this day. Thank you for these students. We pray that you'd allow me to talk. And I just thank you for the weekend that's about to start, Lord. Help us to enjoy this time together, Lord. In your name I pray. Amen. All right. So, I showed you cosets and Lagrange's theorem last time. Basically what we showed was that if you look at the cosets formed by some subset of a group, then they partition the group. All right? In other words, they divide the group into a set of disjoint sets whose union forms the whole set, right? And in the case that the subset is also a subgroup, we have really special properties. Let me just pick some low-lying fruit. This is low-hanging fruit, I should say. This is lecture 13, I believe, right? And so this is going to be on how to multiply and divide groups. We will get to that in due time. There's a couple of tidbits left over from last time basically here. First of all, a corollary, if I were to pick from Lagrange's theorem, if you will, if you have a finite group, if the order of G is less than infinity, then the order of an element divides the order of the group for each A in the group. What's the proof of this? How do you prove that? Notice that the subgroup generated by A is a subgroup of G, right? So therefore, the order of the subgroup, which is, by the way, the order of A by our previous work, divides the order of the group by Lagrange's theorem, right? So Lagrange's theorem said that the order of any subgroup must divide the order of the group, right? For a finite group. Bless you. Another corollary, while we're getting settled, if we take A to the power of the group, we get the identity. All right? This is another easy corollary to Lagrange's theorem. So the proof, notice that let's see here, the order of G, right, is equal to K times the order of A by the previous corollary, right? The order of the group is a multiple of the order of any element. Thus, A to the power order of the group is A to the K to the order of A, which is the same as A to the order of A to the K, but A to the order of A, by definition, is the identity. And so you got the identity to the K power, otherwise known as the identity. All right. So, just going to write a little lemma here, which I probably won't prove. The proof of this is very much like what we did last time. So I'll leave it to you guys. Here it is. HA is equal to AH, or A is equal to Ha, if and only if H is equal to A inverse. So this point 1 in my lemma basically tells us when the left and the right cosets are the same. All right? So the left and the right cosets are going to match up when the subgroup is fixed under conjugation by A. And then 2, which is something I meant to say, it's easy to prove, but it's nice to have for computational purposes, which is that A times H is equal to AH, and H times HB is equal to HB for all H in the subgroup H. Now both of these, I'm assuming that H is a subgroup of G, right? Okay. The concept of a coset is larger than the concept of like cosets created by subgroups, but we have the nicest theorem when in the case that the H is actually subgroup. The proof of this is like element chasing, like we did last time, okay? So let's look at a specific example that I began looking at last time. All right. So here's the example. So I want to illustrate a case where the left and the right cosets are not the same. Okay, so let's see here. We're going to look at S3, which we'll write in terms of cycle notation 1, 1, 2, 1, 3, 2, 3, 1, 2, 3, 1, 3, 2. There's all 6 things in there. And I want to contrast the left cosets to the right cosets. Going to make a little table here. And we picked at this a little bit last time. We're going to let our subgroup be the cyclic subgroup generated by the cycle 1, 3. In other words, it's 1, 1, 3. Right. We saw last time, as an example of Lagrange's theorem in action, that there were 3 cosets here, right? Because the index, how's the index? What's the index? You guys remember? How's it go? Is it G colon H? The index, that's the number of cosets, right? And we said that that was the order of G divided by the order of H. In this case, that's 6 divided by 2, which was 3. So we found those 3 left cosets last time, right? What were they? They were, so on the one hand we have H itself, of course, which is also equal to 1, 3 H. By the way, what you see in action right here is part 2 of the lemma. H basically swallows in elements of itself, right? So like 1, 3 is in H. So it's just, yeah. Let's see here. Excuse me. Ay. Okay. On the other hand, kind of boring. We didn't do this last time, but here it is. Here's the right coset. That's also H. All right. Then we have 1, 2 acting on H. That gives me the set 1, 2, 1, 3, 2, as we calculated last time. Now that also has representative 1, 3, 2 H. All right. So this coset either has representative 1, 2 or 1, 3, 2. Them's your choices. When you calculate the corresponding right coset, all right, H multiplied on the right by 1, 2, what we get is 1, 2, 1, 2, 3. So that's also has representative 1, 2, 3 or 1, 2, depending on what you want to do, right? I mean, just to be clear, this one's also equal to 1h, but that's kind of dumb. But anyway, I mean, sorry. All right, so notice that the left coset and the right coset with representative 1, 2, they're not the same, right? The left and the right cosets are different here. Now, 2, 3, h, 2, 3, 1, 2, 3. So we can also represent by 1, 2, 3 on the left, or 2, 3. These are different representatives for the same coset. Left coset. Now the right coset containing 2, 3, represented by 2, 3 is 2, 3, 1, 3, 2. And again, you have your choice of either representing by 2, 3 on the right or 1, 3, 2 on the right. So all 6 things, right? All 6 things in the symmetric group with 3 letters are covered by these cosets, just in a different kind of collection, right? Like the groupings are different, aren't they? You see the partitions different? Okay. So this brings us to the definition, which I'll explain the significance of as we go on here. But definition, a subgroup H of group G is called a normal subgroup if and only if AH is equal to HA for all A in G. We denote this normality via H triangle G. I guess some people might put triangle with a bar under it, but I'm just going to draw triangle. Okay? In contrast, if you just want to say H is a subgroup of G, we just write this. If we want to say H is a subgroup, right? While I'm continuing this litany of notation, H subset of G is that. See the difference? Normal subgroup, just subgroup, subset. Okay, so obvious example, as I've just calculated here explicitly for you. H, 113 is not a normal subgroup of S3. I don't want to calculate this for you, but it turns out that A3, the alternating group, which is what? What's the alternating group of order 3? Well, it's not order 3, but with 3 things. It's got the identity, right? Say again? 1, 3, 2. And 1, 2, 3? Yeah. That's it. It's half the size of the group, right? That always happens. AN is half as big as SN. And so here they're actually, well, fine, I'll calculate a little bit. What are the two cosets of A3? It's A3 is the one, right? How do I know there are 2? 6 over 3 is 2. The index is 2. There are 2 cosets with respect to the alternating group here. We know that by Lagrange's theorem. So this is one of the cosets, and the only other one to find is what? Anything that's not in here, right? For example, 1, 2 times A3, what would that be? 1, 2, 1, 2, 1, 3, 2, and 1, 2, 1, 2, 3. this will work out to 1, 2, 1, 3, 2, 3. All right? Not necessarily in that order. I just know that those are the things in it by process of elimination. We proved that the cosets partition the group in general, right? If there's two things, if it's not in the first coset, it's in the second one. So I don't actually have to multiply those cycles to know that. And you can calculate, in fact, that this is also equal to A3 times 1, 2. Okay? And in fact, you could, if you're really imaginative here, all right, you could think about these cosets taking on a life of their own, right? You could draw a little Cayley table. You could put A3 here. You could put 1, 2, A3, like this, right? And you could find the Cayley table of what's called the factor group of S3 by A3. And how would I decide how to multiply these? I propose that we can multiply them simply by multiplying representatives, like A3 times 1, 2, A3. So A3 also can be represented as what? Like 1 times A3? Let me make it more exciting, 1, 3, 2, to make it more interesting. So my claim is that that would be 1, 3, 2 times 1, 2 of A3. That might make a meaningful multiplication. We're not sure yet. I'm speculating. What happens when you multiply these cycles? One goes to 2, 2 goes to 1, 2 goes to 1, 1 goes to 3. Looks like 2, 3, A3. Of course, 2, 3, A3 is just what? It's just 1, 2, A3 also, okay? So the product, and this by the way is just A3, right? So the product of A3 and 1, 2, A3 is just 1, 2, A3. And if you work this out, if you take the product of any two things in the cycle, in the coset which is not A3, any product of any two of these, right? Any two representatives in there, what do you get? You get something that's in A3, right? Because the product of two odd product of two odd permutations is an even permutation. So if you take any two of these and you multiply, it has to be back in A3 again. So according to my rule, this would be A3. That looks like a Cayley table. It's got the right kind of pattern. All right. What would happen if I tried to multiply cosets like this for that H? So here's my claim is that if we try AH times BH equals to AB times H, here, in this example, it doesn't make sense as a group operation. All right? Let me show you how that is. So, for example, I could multiply 1, 2H times 2, 3H, and that would give me 1, 2, 2, 3H, which would be what? What is this? 1 what? Is this 1, 2, 3? Let's see, 1 goes to 2, 2 goes to 3, 3. Yeah. So it's 1, 2, 3, H, right? Now, that's not the only way to represent those cosets, right? 1, 2, H is also what? This is equal to that, right? So I can try, oh, I'm sorry, idiot. Over here. Got to keep, stay on the left, okay? Sorry, I'm a Trump supporter. It's hard for me. Let's see here. So 1, 3. I mean, wait a minute. Is Trump really on the right? I don't know where Trump is. I don't know. It's probably at Trump Tower. No, not right now. See here, 1, 3, 2. So if I try 1, 3, 2, H, which should be the same thing, right? These are equal. What happens? What happens? Multiply these. What do you get? One goes to 3, 3 goes to 2. Looks like 1, 3, 2, right? Oops. Why is this an oops? See, 1, 3, 2H and 1, 2, 3H, these are different outputs. So these should be giving us the same thing because what's in blue and what's in green are equal. As far as cosets are concerned, these are the same cosets. And yet the product of these two same cosets produced different outputs. That's not a binary operation, right? It's not single valued. It's at least double valued. That won't work for a product. The reason that's not working is because this H is not a normal subgroup. If you want to make this an operation for cosets, a group operation for cosets, you need normality of the subgroup. That's the significance of normal subgroups. It makes this multiplication on cosets well defined. Yes, sir?
Is that sufficient for the group to the operation to be made as well?
Let's find out. So the question is, if it's normal, is that enough? So definition, well, investigation, let's say. Suppose H is a normal subgroup of G. So AH is equal to HA for all A and G. Yes?
Don't we have an issue with our replication being blue?
What do you mean?
1 goes to 3, 3 goes to 2, then 2 goes to 1. So shouldn't it be 1, 3?
Oh, this is just 1, 3?
Yes.
1 goes to 3. Oh, yes. Thank you. Very good. But as you can see, it's still not the outputs are not the same. But yes, thank you. I should have looked at my notes. Oh well. So what do we want to do? We want to check that this product is independent of representative. Right? That's the thing about cosets, is there's an ambiguity. You have choices of representative. So whenever you're defining something in terms of cosets, we're obliged to show that the construction is independent of the choice of representative. So what we're going to do is we're going to suppose we've got two different choices, right? Suppose AH is A prime H, and BH is equal to B prime H. Hopefully I'll do better than I did on the test with my priming. All right, right? There we go. Consider then that if we look at A prime B prime H, what's that equal to? So here's how it goes. This is A prime. Now BH is what? B prime H is BH. Now, okay, but H is normal, right? So this is A prime HB. So this is by normality, right? And then this is what? Well, this is AH, because we assumed A prime H is equal to AH, right? I mean, we assume that. And now we use normality of H again. So that gives us ABH. I should have used the normality of, of course, well, I'm trying to think. Okay, anyway, sorry. Let me not try to confuse myself. So there you go. The product is independent of the choice of representative by normality. So yeah, that suffices. Now that we know this, we can go off to the races. What's the identity? So is it a group? So our claim then is this, that G mod H, which is the set of cosets, forms a group with respect to the operation that we've just shown as binary. Okay, so for it to be a group, first of all, notice that number one, H times AH is equal to, AH times H, which is equal to H again. I'm sorry, I'm an idiot. AH. So H serves as the identity in G mod H. Now, I'm making a claim here. To actually prove that, I guess I probably should chase some points around and stuff, but I have a bigger story to tell today, so I'm not going to, I refuse to get into those details at the moment. When I write up the notes, I will give you the gory details here, okay? If you can forgive me for omitting them at the moment. What's the inverse? I mean, there's some details missing here, okay? What's the inverse? If I take A, H, right? And if I multiply by A inverse H, why does A inverse exist? It's a group, right? So its inverse exists. And so this is equal to, by definition, AA inverse H, right? But AA inverse is the identity. H is a subgroup, right? E is an element of H, right? Since E is an element of H, E gets swallowed up into H, right? That's part of 2. Or the theorems we proved last time. So there's an inverse. And you can go either way, the right or the left, right? So the inverse of the coset is the coset with the inverse representative, right? What else do we need? We got identity. We've got closure, because this over here was binary operation, right? I guess I also need what? I need that, I guess I need that AB is a coset, but that's clear, right? I mean, that aspect of closure is clear. The complicated thing, the non-obvious thing is the well-defined, right? But we've settled that here. You said identity, what else? Associativity, right. So 3, if we look at AH times BH times CH, that will be what? AH times what? BCH, which will be equal to A times BCH, right? But by associativity in the group, that's equal to AB times C times H, which, of course, is going to be AB H times CH, which, by the way, is going to be AH BH parentheses times CH. But that holds for all A, B, and C, so there you go, associativity in the quotient. It follows from associativity of the group, right? So I told you I was going to tell you how to multiply and divide groups today. This is how we divide them, okay? You can only divide, in some sense, if the group is a normal subgroup. What are examples of normal subgroups? I got carried away with this one. I had a few other low-lying ones to pick up in here. A really big one to think about is if my group's abelian, right? If G is abelian, then H subgroup of G, what do we have? We have A plus H, right? Which is A plus little h such that H is in H, but that's exactly H plus A such that H is in H because it's an abelian group. So we can commute the operation, right? And that is straight up the right coset of H, isn't it? So in an abelian group, the left and the right cosets automatically are equal in the sort of simplest way. So every subgroup of an abelian group is normal. And that means we can form the factor group for any subgroup in an abelian group. It's very forgiving. It's not like the symmetric group where we have to be careful what kind of thing we divide by. Okay. Are there other examples of normal subgroups? Well, yeah, sure. I've got a few more. Gallian's list is pretty nice. For essentially the same reason, you can argue, I will forego the details at the moment, but I'll just mention for your informational purposes, the center of any group is normal. Some of these things we'll come back and prove in later lectures. Although that one's almost immediate from the definition of center, right? If you think about the center of a group, it's what? It says, yeah, it's a set of group elements that commute with all other group elements, right? So that pretty much forces normality of the subgroup, the center. Another example. So the alternating group is normal. If you look at the group of rotations inside the dihedral group, that's a normal subgroup of the dihedral group, essentially because xy is equal to yx inverse, using our usual generators and relations notation for dn, all right? A more exciting example, something I noticed actually in the course of another lecture, is that SLNR is in fact a normal subgroup of GLN. Remember what SLN is? SLNR is the set of matrices, what? Right, A in Rn by n, such that the determinant of A is 1. Oh, there's a theorem I neglected to state. Theorem. Well, did I state it? I guess I have it here. The theorem just says, the theorem is a little bit sneakier. The theorem says this. It says that AH is equal to HA provided that AHA inverse is a subset of H. So that's a little bit nicer because this is theorem 9.1. Because that just requires us to get that the conjugate is a subset of the group, and I don't have to go the other direction. Although I think showing that H is a subset of A inverse might be kind of trivial anyway. Okay, so we're going to use that theorem here to check for normality. So what I want to do is let's say M be an element of SLNR, right? And well, that's not what I want. Excuse me. I want to let's say B be an element of A SLNR A inverse, right? So that's like my A H A inverse in the theorem, okay? And what's the determinant? So that means that B is equal to A M A inverse, where the determinant of M is equal to 1, right? So what's the determinant of B? Now here the A is just an arbitrary thing in GLN, all right? That's what I was complaining about the other day. Not really complaining too strongly, but he has another example somewhere where he assumes that the conjugating matrix is in the special linear group. But the calculation works when the matrix which is conjugating is in the general linear group. It doesn't. You don't have to assume determinant 1 for this calculation to go through. See, these cancel, right? And so that's 1. So this is equal to 1. So therefore, B is an element of SLNR, which verifies that A, H, A inverse is a subset of H, where H is the special linear group. And A is arbitrary, therefore, the special linear group is a normal subgroup of the set of all invertible matrices. So that's a neat example, I thought. Don't ask me to show you the factor group there. All right. Now, so now we know a little bit about how to divide groups. I've shown you an example of what not to do, and I've shown you an example of what to do. There, of course, is much more to say about factor groups, but I'm trying to get everything out on the table here at once, and then we're digging deeper and deeper into it as we go on. You know, there's tidbits in chapters 6 and 7 that I haven't covered yet, right? And I'll come back and get those in due time. This, what I'm doing right now, is chapter 9. I'm about to be in chapter 8 here in a second. So I hope you understand I'm not covering the book quite in linear order at the moment. So, excuse me. So, external direct products. Here's the definition. G1, G2, Gn, finite collection of groups. All right. Then, and unfortunately, I used the wrong notation in the help session at one point. I had the, well, I'm going to get them both out on the table here, and then we'll talk about, I'll show you the difference in a second here. Then this is the external direct product of these groups. What this is it's a set of n tuples, G1, G2, Gn, such that Gi is in big GI for all I. Right, so as a point set, right, as a set of points, it's simply the Cartesian product of the groups, okay? The way we multiply in here is as follows. If you got G1, G2, Gn, by definition, we multiply that by another thing in here, H1, H2, Hn. All right, by definition, we just multiply component-wise. G1, H1, G2, H2, Gn, Hn. So this is a group. You can prove that this forms a binary operation. You know, I'm going to skip the details here at the moment. The identity, for example, what's the identity element? It's E1, E2, En. It's the Cartesian product of the identities of each of the groups that you're forming the direct product of. Okay. Let me show you an example. Example. If I look at the direct product of, say, Z2 and Z3, what's this going to look like? This is going to look like two tuples, 0, 0, 0, 1, 0, 2, 1, 0, 1, 1, 1, 2. That's fun. Not sure, is that Thank you, Nathan. Mucho appreciated. If I'm a glutton for punishment and I actually have time, we can draw the Cayley table for this. Oh, I'm going to regret this. Now the way this works, right, is if you look at AB, this is done mod 2, this one's done mod 3, right? So when I'm, and the operation is addition, all right? Because Z2 and Z3 are additive groups, right? So, you know, let's see here. 0, 1, I'll do the second row. 0, 1, 0, 2, looks like 0, 0, 1, 1, 1, 2, right? We got 1, 0. If I'm right, we should only have one of each in every, right? Do I have any repeats? No, it's good. All right. Here, I'll do this column. This is 1, 1, 1, 2. That's 1, 0. 2 is 0, right? So 0 in the first spot. 0, 1, 1, 1, 0, 2. Sorry, I'm going to stop this in just a second. 1, 2 plus 1, 1 is what? Oh, that's 0. All right, enough. Anyway, you can keep going with this. This is the direct product of Z2 and Z3. Okay. There's something else, though, all right? There's something called an internal direct product. What's that? Was it? The internal direct product. Oh, and by the way, I just showed you how to multiply groups, if you're wondering. This is how you do it. Okay? You got two groups, you can put them together, make a new group, the direct product, just like that. Easy peasy. Definition, if G is group with normal subgroups, H and K, and G is equal to HK. You're like, what is HK? Very good question. How would you define HK, guys? So what this is the set of all possible products in H taken from H and K. All right, so it's like, you could write it this way. It's like H to the K. Oh, bad choice. H to the I, K to the L, such that I and L are in Z. All right, just all possible products, something like that. Right. I think I got that right. But anyway, if this is the case, if all of this, then we say G is equal to H cross K. So this is the internal direct product. Now, I don't know. I really don't like this notation. Everything in me wants to turn these over and make that one with the crosses and this one with the plus, because that's what I do in linear algebra. In linear algebra, I use the plus with a circle when you have two subspaces whose direct sum forms the whole space, right? And I don't know. This notation is never agreed upon by everybody. Anyway, this is the notation Gallian uses, so it's the notation I'm using in here as to not confuse you, all right? Or it can confuse you less. Now, example, Z6 is equal to Z2 times Z3. If you think about this, right? If you have Z2, Z3 would be equal to, how can I say this? Oh, that's wrong. Why are they so, why are people so ignorant? I tell you. Anyway, no, I do mean equality here, not isomorphism. So Z6 you can form as the product of the subgroup generated by 2 and the subgroup generated by 3. And let's see, so that's like 2 to the 2 times k plus 3 times l, such that k and l are integers. If you look at that, that's what it looks like. That's what this is in the additive notation. You can easily see by different choices of k and l, you get all of Z6, right? Because 2 and 3 are relatively prime. So as k and l, I mean, you can hit anything with this. You try it. You'll find that you get Z6 from here, okay? I promise. And the intersection of the cyclic subgroup generated by 2 and cyclic subgroup generated by 3 is what? It's 0, right? Yeah, so this fits the bill. Z6 is the internal direct product of Z, that was what you were asking about isomorphism, wasn't it? It's the internal direct product of this and that. Thank you. Sorry, eventually I will see my error, the error of my ways. It is true, right? In fact, you could draw a Cayley table if I had more time. We could draw a Cayley table for Z6, right? And you could compare, and you'd see that the pattern matches. And in fact, they are isomorphic. This is isomorphic to Z2 direct, external direct product Z3. Anyway, these are the kinds of isomorphisms and patterns we want to understand more deeply as we go on in here. So I've assigned you some homework to get us started in that project, but we won't really finish this project of understanding quotient groups, or factor groups as they're called, and the direct product, internal or external, of groups for a few days. It's going to take us a while to really wrap our mind around these ideas properly, right? But I want us to get us started today, so I did. I'll end 2 minutes early in an unprecedented fashion.